great to see everybody in person for the first time since 2019. It really is just a real pleasure to be here and to have everyone here. And thank you all for making this trip. It really is great. The plan for this week is to, when we got the renewal, just to give you a little background for the R25 that we are so grateful for that funds this project, we had this brilliant idea that we would do every other year, sort of intro and advanced. And the first year of that, we got hit with COVID, and we were out since that was supposed to be 2020, and we haven't been in person since. So now we're kind of like rolling everything else up into one now. Hopefully some folks have had a chance to see some of the online things. The silver lining of the cloud, if you will, of all the COVID was we have a great sort of resource now of video presentations that people should help themselves to at any time. But we're now in year 4 of a 5-year renewal, and so we're going to cram all of those sort of pieces into 1 week. No, seriously though, the plan today is assuming that most people for this week this is the first of our intermediate/advanced sort of program. And so the assumption is largely that most people have some experience with social network research and understand the basics of what's going on. And if not, that's kind of what today is for. And so you're going to get the world's fastest introduction to networks, reminder of what network analysis is about. And that will largely me. And then we're going to introduce you a little bit to some tools and practices. And so Leanne is going to give some work on introducing people to R who have not used it before, or reminding those of you who've used it infrequently some of the tools that come out of network analysis. And then we're going to show you a little bit of self-bragging. We have a new project called IdeaNet, which is a software tool we're developing to try to make all of this work easier to do. And so we will show you what that project is like and hopefully get some of your feedback on how to make it better. So that's kind of the plan for today. Over the course of this week, we have the week set up roughly around some themes. And so tomorrow is our data day. And so we're going to talk mainly about data for the first half of the day. And we're going to talk about different ways in which you might collect data with ego network data, video data, and sort of general survey types of things. And then we're going to talk a bit about description. So data and description are going to be largely what the day is. The afternoon will be community detection and things like this. And then on Wednesday, we're going to really focus in on implementation and experimental methods for networks and health. And so we have a wonderful morning set up with a panel of people who have really done the get your hands dirty kind of work of implementing interventions for health using network tools. And so there'll be one series of presentations that Tom Valente and Nina and Yamal will be part of, and that will be focusing really squarely on the health side. And then the second session will be on field experiments or lab experiments. And so the first one is on implementation in the health spheres. The second panel is on experimental methods with networks. And then the afternoon is going to be spent talking more about different kinds of models of networks. So how do we deal with what is the theory and ideas for pushing networks and health into the world? And so we'll talk about peer influence there. We'll talk about some ideas of roles and role networks and things like this. And then on Thursday is our stats day. So you got 2 days to warm up your mathematical pens and remind yourself what a standard deviation is. And then we'll end up coming in on Thursday, and I will give us a brief primer on, probably an hour and a half or so, review of what statistical methods are, and we'll go through all of those. And then it'll be a great day because I think there's been a lot of new things that have happened since I saw many of you last time in this course with respect to the exponential random graph modeling framework. They've been having an entirely new syntax, and it's generalized now to many more sort of applications that you can use, either as a generative feature for simulations or as an estimation feature for thinking about things. And we'll get to learn some new ideas throughout the day. And then the final day on Friday, we'll have a half day in the morning to complement the day, and that'll largely be centered around thinking about this notions of diffusion, particularly the disease context. So we're lucky to have Sam Jensis in, and he's going to talk a bit about the epidemiological modeling. I'll talk about some agent-based modeling and simulation modelings for diffusion, but it's all about essentially how does a person get a bug from someone else. And so that's a big overview of it. Every day, except for today, we will have a lunch, and the lunch will be provided. It'll come here from Panera. and where we will do a lunch talk. And the lunch talk is supposed to be a little bit different than what we normally do, right? And so it's supposed to be less about sort of the bread and butter of networks and health, and more about how networks are interesting throughout the world, and there are different things we can learn about networks. And so we're really pleased this time that we're going to have, we'll do an ethics discussion tomorrow. Dana Pasquale, who many of you know, I don't think Dana's here right now. Dana is going to talk about data archiving, sort of generally, what do you have to do to get data stored in light of the new NIH requirements. And then on Thursday, Robin, who I think is it, Robin is here, is going to introduce us to networks and linguistics, which is just fascinating, and I really hope you'll all be able to stick around for that. We'll have coffee sessions both in the morning and afternoon, just so that people can wake up and remember where we're at. I encourage you, we have posters set up here in this first hallway. These are all from some of our returning fellows and other people that are related to DNAC. And these are just there really to provide conversation starters. So just have a chance to look at them and look around and seek out the authors and see what they're doing and get more information on what they're presenting, so you can get a sense. We're going to leave them up all week, and so you can focus on that. If you have a poster of your own that's not up there and you want us to share it with us, let me know, and we can find a way to get it printed for you. So that would be there as well. What else to say? We're very grateful to the National Institutes of Child Health and Human Dynamics and ICHD for funding this project, and for the Duke Population Research Institute, Dupree, who's our co-sponsor, with the Duke Network Analysis Center. There's a lot of Duke Blue running around this organization, so we really do appreciate all of the help that they've done for this. We are guests in this space of the IID, which is the Rhodes IID, is our Data and Information Sciences group. So be good guests. They let us eat in here even though we're not supposed to. So if you spill mayonnaise on the floor, let us know and we'll make sure that it gets cleaned up. But otherwise, just be responsible. What other kind of housekeeping things to keep in mind? We have masks everywhere. The pandemic's over, but if you feel ill, please check us out online and don't come to class, right? Please, pretty please. And if you feel like being in a crowd for the first time in 4 years, it freaks you out a little bit. Like I said, we have masks around, and that's perfectly acceptable as well. Other questions or comments on sort of general mechanics of things? I think you should treat this a bit like a Protestant congregation, right? Make sure you shake hands with somebody you haven't met. Turn around and introduce yourself. Think of maybe sure you're going to go out to potluck later, that kind of thing. So, this is the kind of opportunity we're in. If there's, for every meeting, as Durkheim used to say, there's always a latent and a manifest function. The manifest function of this particular organization is for us to get together and learn some social networks and health, but the latent function is so that we all get to create a community and recognize each other as what we are, right? So make some new contacts, make some collaborators, learn who you're working with, and maybe hopefully some new grants and ideas will come out of this. All right. All right. Any other sort of housekeeping things to go? All right, let's jump into some actual bits and pieces of what network analysis is then. So I'm going to do all three parts of this in the next 2 hours in more or less detail. This is why I say it's going to be the world's fastest reintroduction to social network analysis. For those of you that are truly new to this, just hold on, you'll be fine, and it's all recorded and it'll all be online later. You can get it if you want. Let's just start a little bit with networks and health. So social network, the reason we started this is that there's a lot of people now that are working on networks and have been working on networks for a long time. And the growth in this field has been dramatic. And the networks and health side of it has gone up really fast as research on sort of other sorts of processes that health people spend a lot of time and concern thinking about. And NIH and NSF continue to fund this at increasing rates. And there's lots of money and lots of grants going into this. And so NIH thought it would be a good idea to provide some training to support all of this work and to provide reviewers to review some of these grants. So that's the sort of the background. Like I said, this was going to be fast, right? So this is like all you're getting. No, that's not. I'll do a little more background. But that's essentially the thing that drew us into working on this. Just to set a little bit of common language, for us, network analysis, social networks are not social media. So there are some networks embedded in social media, but social networks are these human social relations that connect one person to another or a person to an organization or an animal or something like this. But there's a relationship mapping process. And social networks capture a set of relations that's motivated by this structural intuition that's based on graph theory. So you can think of it as applied graph theory. It's grounded in systematic empirical data and relies heavily on these computational tools. And the reason we're sort of in this room is those computational tools tend not to be taught in your standard sociology or social science or health science classes. And so the goal is to help give us a sense of what these tools are like so we can use them effectively. The reason we care about it is that networks have this really interesting property that instead of thinking about individuals themselves, we can think about how an individual is embedded in a community and how any effect on an individual spreads out to others. So there's this natural spillover effect. And this spillover effect with any kind of thing you tend to do in the world, we nicely ignore when we do our methods. So if you ever try to set up a clinical trial, you have to make sure you have your control group is never contaminated by your treatment group, even though you know in practice that any public health treatment you give to a particular person is they're going to talk to it at their family, they're going to talk about it at their job, and so forth. It's just going to spill over. And so we set that aside artificially whenever we do research, but in practice it has to exist. There has to be this spillover. What network analysis tries to do is map the spillover. We try to figure out like what is the process that creates that contamination and how do we essentially use it to our benefit as opposed to have it used as sort of treated as noise. The history of the field of social networks and health is fascinating, and Ashton Verderay and Alex Chapman and I have a nice paper. I think it's a nice paper sort of going through a lot of this history. I encourage you to look this up at some point if you'd like. It goes into much more detail than I will here. But briefly, the idea is that the growth in this field is keyed to a set of landmark papers and a lot of landmark papers. And I want to just give you a brief sense of what some of those are. Probably the first founding idea that sort of pushed a lot of this work out is Everett Rogers' Diffusion of Innovations. This is a really nice book because it sets the groundwork for different types of diffusion processes. And we tend to think about disease diffusion, especially for the last few years, but the idea of an innovation diffusing through a population or an idea diffusing through a population in the same way that a disease moves was actually kind of a unique idea that Everett Rogers put forward. And he flipped the script a little bit and said that you don't have to think about it as something that passively moves through the population, but it's something you can actively push through a population if you understand what distinguishes an adopter from a non-adopter and how these kinds of adoption thresholds change and what we might do to influence these adoption thresholds. Within the actual sort of social networks and health idea, this was work coming out of Berkman et al. Has really focused on the ways in which social integration leads directly to health. And so it's not just that things move through health, but being integrated in a social community creates a system and a sense of support that actually leads to increased longevity. And so this had this paper was a hallmark because it's marked so clearly actual changes in life expectancy due to integration in social settings. My own sort of entry into the world came from as a young graduate student working with John Potterat and Rich Rothenberg on some sexual network work. This was where I first became exposed to much of the work on networks through STD and HIV. This was coming out in the late 90s. The work that they were doing, the data they collected were in the early 80s. John Potterat is a remarkable machine in terms of data collection. And he spent many years embedded with commercial sex workers in, that doesn't sound right, but you know what I mean, as a public health worker in Colorado Springs, and he collected some of the best data to date on detailed sexual networks and drug sharing networks in a real community. And so what he really did well, and with Richard Rothenberg, was demonstrate that it's possible to collect this kind of data that everyone said you couldn't do. And by so doing, it gave us insights into what the structure of those networks look like in ways that you'd never see otherwise. This also then, once you get these kinds of data, you end up thinking about questions in new ways. And Martina Morris, about this time, introduced an idea based on these data and some other data she was collecting in Thailand at the time, of this notion of shared partners in time. And it changed the way we think about networks, not in terms of just a series of connections, but a temporal unfolding of relationships. And that temporal unfolding, it turns out, is crucial to understanding how diseases move. And the two settings with the same contact pattern, different timing, can have dramatically different spreads in disease spread. Of course, there's sort of, you all know Roy and May now, given that all the work we've done recently on diffusion models, and in Bauman's work on peer influence. I'm going to move through these quickly in the interest of time. A few others, AdHealth, StatNet, Christakis and Fowler probably is the most recent big picture piece that really kicked off in the popular imagination that you could have a network effect on health. Their argument that obesity was contagious really ticked a bunch of people off. They thought this was not a good idea. The economists threw a fit over this election idea. But the idea stuck, and it stuck because at its root, as many arrows as you threw at this thing, it really kind of works, and it works pretty well. And the modeling, and we've come a long way in the modeling since this paper came out, but the general idea has withstood the test of time. And moreover, you've been able to flip it around and turn it again to say that we don't just have to observe this happening passively on a network. We can introduce it to the network and help make the population better by exploiting the kinds of connectivities we see there. And I'll go through the rest of those. All right, so if you think about the ways in which this field works, one of the tricks that Ashton and a few of the rest of us do is to do these things called text networks. And in a text network, what you have is some given paper, and it's linked to other papers by semantic similarity, by the overlap in words is the easiest way to think of it. They're weighted in various and sundry ways, but for our purposes, all that matters is that you have two papers are close to each other if they have a lot of things in common. They're far apart if they don't. And if you map that out big enough, you get what we call an intellectual landscape. And so this is the intellectual landscape of social support, or of social networks in health, excuse me. And the paper I was just using that little example is right there. And then what you can do is you can look at across this landscape. It's not an even just spread of papers. Instead, what you see is that there are these clumps. And these clumps relate to clusters in the network. And that's not going to work. I lost my clusters. These clusters each sort of capture a system or a set of papers that are all in the same thing. So as you might expect, there's a whole cluster of papers that are studying HIV, social capital, social support. These are very big sort of gorillas in the room kind of areas. But what's nice about it is once you get this kind of piece, you can ask, well, where are the methods we're learning today or this week fit across this topic space? And what's interesting is that a lot of these core papers really find their way all over the place. So something like Rogers' diffusion of innovations is cited at every space in this landscape, right? So whether or not you're studying influenza or you're studying social support, Rogers is important for what you do. Similarly, some of the work that Tom Valente has done on interventions sort of is spread all over the place. Christakis and Fowler's work has been a touchstone. Similarly, with Martina Morris's work on concurrency is clearly important to HIV, but it has tentacles that's moved out for other sorts of processes throughout the landscape. Now, there are some things, like organizational effectiveness, that is really sort of squarely within the health systems cluster, but other things sort of move in. And ad health, for example, is studied in adolescence. You can do it with topics. What I want to point out, I'm hoping you get out of this, that's where gender sort of fits. There's not much on the systematic, what I would call sort of the structural sexism. You'd expect to see that over here, but it's pretty blank. That might be an opening that people could work on. But generally, you find that social networks and health covers a wide range of diverse topics. And that's what I really wanted to just seed to an idea right now. That's really as much of the general background as I'm going to do about sort of, I kind of assume most of us are here because we care about social networks and health, but I want to stop quickly just to see if there's questions or thoughts on the motivation for a workshop like this before we go on to some of the nuts and bolts. I talk fast. I think many of you have heard this joke already. I talk fast, but you're smart, so I assume you can listen fast. If that's not true, let me know, and I can take care of that. Put on pump. All right, all right, let's jump quick then to some of the backgrounds of general network theory. And those ideas are going to sort of run throughout the rest of this week. When we think about doing network research, it's really not that different than you would do for any kind of research. You can think about it as this basic research process. You start with a question, you then get data to answer that question, you then go into this little loop of creating metrics and figuring out what the answer is. It's called exploratory data analysis. Once you get this figured out, you usually generate some kind of a model, you get the results, and you go home and do it again. And so this general process is what we do for any kind of research. What's interesting about network research is that we have sort of a specific set of tasks which usually go with each of these elements, right? And so what a lot of this week will do is talk about a particular element of this. And so in the base course, we spent a lot of time talking about centrality, for example. This week, we're going to really go deep into more of the modeling elements and a bit more in terms of the exploration and clustering elements. But essentially, this kind of a process works wherever you're at. If you really want to play with this idea and learn more about it, I would like to draw your attention to a new book. Craig just left. Oh, that's too bad. Craig, man, we have a new book coming out on network analysis, which really takes all of these ideas, puts them into what we hope is a good, clear way of providing an understanding of these ideas, and integrates them directly with R. So the book includes not just a text for all the text of network analysis, but also a series of integrated labs and R sample code that lets you do all of these analyses as you go on your own. So effectively, it's this workshop, not just limited to health, but limited to everything else, and we will hopefully keep it updated so that your R doesn't crash. All right. So I like to think about networks essentially as in two different modes across multiple different levels of analysis. So the first mode is the modes are on the rows, and the types of analysis or the levels of analysis are on the columns. And this distinction between connectionist approaches and positional approaches are, I think, sort of the foundational, West Coast, East Coast divide, if you will, in social network analysis. And so connectionist approaches are networks as pipes. This is the idea that a network matters because of spillover effects or diffusion or something that's moving through the network takes me to somebody else. And so this is by far the biggest thing about networks that everyone knows about. It's the thing you know about because you lived through a pandemic. It's also the thing that you know about because everyone in your sort of statistical world says you can't do network analysis because your cases aren't independent of each other, the errors are linked to each other. And that creates a diffusion of their error terms, and all your statistical inference is wrong, right? So whether it's a problem or a feature, this notion that things are linked to each other, and thus the thing you care about spreads through those linkages, is part and parcel of the connectionist model of networks. And we're going to spend most of our time, as reflected in the rest of the field, thinking about the connectionist model of networks. But I want to sensitize you to the idea that there's more to networks than just networks as pipes. There's this notion of networks as positions. And a network as a position is the idea that a role is encapsulated by a set of exchange relations. So teachers provide instructions for students. Cops provide handcuffs for robbers. Right? Stores provide goods for customers. There's this linkage of an exchange between one person on a side of a role and another person on the other side of the role, and whatever they exchange is a linkage. And if you have enough of these patterns of exchange, you can create a position that is characteristic of a way of being in a society. And that means that really what the network is doing isn't so much spreading a bit of information, it's shaping a way that you think about and engage in the world that you're in. If you were to think of, and I hesitate to use this analogy when there's an actual linguist in the room, but if you think about the connectionist notion as a network as, say, a paragraph or a story, this networks of roles is the grammar that drives the language. Right? So this is the story you learn from reading the sentence. This is the grammar that drives the sentence itself. Right? It's that kind of an idea, and hopefully that'll make sense when we get there later. On the columns, we can think about networks moving through local networks, right? Just the people you're directly connected to. My family, my friends, my coworkers, right? So these are ego networks or local networks. These are incredibly useful, right? And the data is often easier to collect than the kind of data we're going to spend most of our time talking about, which is what we refer to as complete networks, or networks where you have some set of relations on everybody of interest to your sample. So there might be everybody in a school, everybody in a community, all nations in the world, something like that. There's also now much more interest being given to collections of networks, which we're going to call multiple networks. So you might have 100 different schools or 50 different villages, or families across 300, or a sample of 300 family networks, right? So each of these networks then is collected, and you want to think of them not just as describing the patterns in one network, but you want to figure out what's common across all the networks and what creates distinctions, what's within and between these different multiple networks. All right. So I already talked about this a bit, but the classic notion of a connectionist model of networks is that we care about how things move through the network. And so the fundamental idea here is the notion of something like a diffusion coefficient. And so we can think about R0, the reproductive rate, the number that's been sort of burned into our heads over the course of the last 3 years. And this is a function, as you might expect, is the duration of contact, the likelihood of contact, and the duration of infectiousness. This is the equation from a network standpoint of R naught. And this little thing, connectivity, is the network. And I've given you this, many of you have seen this image before, but if you were to imagine a sexual network, each person that we've sampled has 2 sexual partners. If we want to understand where a disease might flow in this network, it's really not enough to know that each person has 2 partners. Instead, we want to know how those partners are connected to other people's partners and so forth. And so this is from Ad Health. This is an actual high school sexual network, romantic network. And so this kid has 2 partners, but that partner has another partner, has another partner. This is the graph that your mother said that you should be afraid of, right? So everyone you've slept with has slept with someone else and slept with someone else. And what you hope is that you're down here somewhere and not up here somewhere, right? The positional idea, on the other hand, says that we think about networks as this pattern of exchanges. And so if I give you this network and I say that there are 2 people that exchange romantic love and they feed 3 people that fight with each other, you might think of this as your classic cartoon family network, right? And so you have parents and children, and hilarity ensues when they do whatever it is they do. What's interesting, of course, about this is that you don't need the labels to know what this is. And that's what the positional model does. The positional model says, if you give me a series of exchange relations, that social systems will organize those systematically. They will come to some regular reoccurrence. Right? They're not just randomly distributed. And that regular reoccurrence is the implicit social knowledge that people have about roles, and thus we'll end up creating sort of clusters of people that have the same thing. Please. Yeah. That's a great question. The glib answer is about 10 years difference is really the only thing that's different. Is a multi-layer network is a multiplex network, and we would have called it that 10 years ago. But somebody came up with the idea of a multi-layer network, and multiplex networks are effectively a special case of multi-layer networks. The main difference is that in a real multi-layer network, or in one where the difference is meaningful, is that the different layers in the network, say kids and parents, are of a qualitatively different kind. In a multiplex network, what you have are different flavors of relationships among the same set of nodes. Right. Exactly. In theory, yes. Okay, so we're going to get to that in just a moment. Now, the positional network has this, the idea has this really this notion of identity. And this is why I think it's one of the things that hasn't been done a lot with positional approaches is focusing on local networks. So that cell of ego networks and positional tends to be pretty thin in the kinds of work that people have done historically. And so I'm throwing this out for you to have a look at it because some of my favorite work of this has been what Bria Perry and Bernice Pescosolido have done, thinking about the patterns of relations people have across their different social contexts. All right, so there is this class, I'm going to throw a little bit of wider theory out there for you because I just can't help myself, that there's this classic structure-action tension in network analysis. That part of what we care about for networks is we have these beautiful objects that we create and they seem real. There's a structure there. And so this structuralist tendency is the sort of the structural anthropology roots of social network analysis. These strong structures usually carry with them this idea that actors follow a set of rules and they do whatever the network puts them to do. And this comes with this problem that says that actors are cultural dupes. And so if you have a really strong model and structure, actors don't tend to do much. They tend to just follow the rules that are given to them. On the other hand, we expect that these relationships create resources for people that they can draw on and use, and by using those resources, they can actually be effective in the world they're at, and that's a very agentic point of view. And so these two things are in tension with each other. So the agentic model of people doing things with resources at their own choosing, and people being locked into a structure by the pattern of relations around them, are kind of in fighting with each other in the theoretical sort of movements that come out of social network analysis. I think this is a good tension. I think it's a generative tension. It helps us think about the way the world is going along. But just be aware of it as you're dealing with your hypotheses and trying to understand the world you're in, that these two things can often be at tension with each other, and your job is to try to figure out what's going on in any given setting. Right? Is an agent creating relations, or are they the result of those relations? So there's a cause or effect kind of common here. This notion of multiple levels for positional analysis, I'm going to leave aside for now and just jump on to the points and line sets. Any big picture questions about, again, a lot of this should be review. How am I doing on time? Okay, we're doing good, we think. All right. So I'm going to now just move over to really the nuts and bolts of what network analysis is. All the rest of the theory things that we've sort of talked to up in this point, the history bits, those are sort of academic interest. If you really want to do this research, which is I assume you do, which is why you're in this room, then you kind of need to get some data in hand and do something with it. The basic data that we deal with are a joint data set of nodes and edges. And so the nodes part of the data set are your actors, your organizations, your people. These are the things that have relations. For most of us, these will be people. But they could be organizations, they could be viruses, they could be any entity that is connected to some other entity. But most of the time, we will refer to people. Now, because social network analysis has been growing up across math, across computer science, physics, all kinds of different fields, the jargon in the field ends up being pretty ridiculous. So we hear nodes, actors, vertices, like all of these mean the same thing, right? These are the ends of the lines. And then relations connect them. And so the node part of the data set is something you've been using if you're a social scientist all your life. So this is just a rectangular data frame where each row is an observation, each column is a variable or an attribute, and you can have as big a data frame as you want to describe nodes, right? That's the standard bread and butter of every social scientist. The relationships, on the other hand, link them together. And whatever index you have connecting your, identifying your nodes, a pair of those becomes an edge, right? Now, relationships take on multiple forms. You can have the basic underlying set, which is an undirected binary network. And this just says that two nodes are connected or not. So it's either present or absent, right? And so in a meeting together. And so are related would be a necessarily symmetric relationship. If I'm in a meeting with you, you must be in a meeting with me. Co-presence requires it, right? Unless something weird is happening. A directed binary network says that there's a difference between what I do to you and you do to me, right? So if I say hi to you, you might not say hi to me, right? And so speaking to is a directed relationship. C speaks to B, B snubs C and doesn't respond. We can also value these ties, right? Either by the number of times that something happens, or if you're graphically doing it, by the thickness in that set. Now you can have multiplex ties, and this is the discussion we were having just a second ago. If you have the same set of edges, you can have many relationships layered over those edges, right? So it's possible that we can be friends and coworkers, perhaps harder for academics if you've ever been in my department. Or that's a joke, I like my colleagues. I'm just trying to make sure you're still awake. And so the multiple relations just get stacked on top of each other. Right? So you can be friends and colleagues, you can exchange advice and so forth. And in fact, this is arguably what makes social relations interesting and a little bit different than just pipes, is because you can be multiple things at once. And whether these things are in conflict or not is kind of interesting. And if you go to the levels of analysis, we already talked about this a minute ago. Ego networks are where data that you collect where you have a single individual and their respondents. Oftentimes, their interlocutors, their contacts. Oftentimes, those contacts are reported by ego, right? So you'll survey me, and I will say, my 5 best friends are Joe, Mary, Jill, and Jane. So I have 5 friends, 2 of which are named Jane. But notice what that is, right? That's just survey data, right? So that's data that we all know how to use. It's a single respondent and a bunch of questions, and we want to combine those questions in an interesting way. But the beauty of that data is you can collect it with a standard survey instrument, right? And so it's ego and the people they're connected to. Now, if you're really lucky, you can get that data from them, right? So I interview a person, I say, who's your friends? And then I go out and I interview those friends, and you get some confirmation on the information. But you can do a lot with just the things that the respondent says about their alters. A partial network is anything sort of bigger than just the ego network, but perhaps not the entire setting that you're interested in. So if I'm interested in all sexual networks in Chicago, right, I'm unlikely to actually survey everybody in Chicago, right? But I might sample a few people, ask them about their partners, and then ask them about their partners, and snowball out a ways. And there's a lot of ways you can do that. You can do snowball tracing completely ad hoc, right? Just get anybody who will answer your survey. Or you can be a little more systematic, and there's what are known as adaptive sampling routines or respondent-driven sampling routines, which allow you to weight this snowballing in a particular way, and that weighting allows you to infer to the population in a nice way. And we'll hear a little bit about that. I don't think Ashton's going to talk much about respondent-driven sampling. On the other hand, we have what we call complete or sociocentric or global networks. These are all terms for the same thing. But the idea here is that you have relations, you have a fixed set of nodes, say all kids in a classroom, and then you're interested in all possible relations among those sets of kids. So all clergy in North Carolina, all Supreme Court justices in the United States. So it could be a small set, there's only 12 of them, but their relationships are somehow what was of interest. Now, oftentimes our theoretical frame isn't the same as the frame that we can collect. So for example, if I'm talking about sexual networks, I might be interested in all sexual networks in Colorado Springs, and John Potter did a great job, but he didn't get them all, right? And so we know it's an incomplete data set, but we're going to treat it as if it's a global network anyway. All right. And this is I'll go through that the other way. Excuse me. So another way to think about data, about network data, is a distinction between the number of modes of connection. And so a one-mode data set is the standard that we've been talking about thus far. And in a one-mode data set, each person or each node in the network could connect to any other node in the network. There's no logical distinction that makes it impossible for one node to go to the next. So in theory, any kid can be a friend with any other kid in high school. Right? There's nothing that makes that impossible. In a two-mode data set or a multi-mode data set, there's some distinction between the nodes that means that relations only happen across nodes, but never within modes. Right? So you might, for example, have authors and papers. So authors are linked to papers, but papers are not linked to each other, and authors are not linked to each other, except through the fact that they shared a paper together. Right? And so these kinds of people as member of groups, or words used by people, or events in the life history of people, these are two-mode networks. And the beauty of two-mode networks is they are everywhere, right? People attending a meeting, people answering a question on a survey, anything that you can link a person to becomes a two-mode network. And what's nice about it is that, come on in, what's nice about it is that anything that you have, then you can turn into this network frame. And the joke that I always make to my students is that I'm a network imperialist, right? In the sense that I will turn everything into a network if you give me an opportunity. I'm also a network empiricist, but that part sort of comes later. And so, like, literally, I can turn any problem into a network problem. And I think usually profitably, sometimes trivially, but most of the time profitably. Once you have a multi-mode network, you end up with the capacity then to treat it as is. I can just analyze it as a in this case, which is known as a bipartite network. I have two parts. That's the bi, so I have the events and the people. And if you analyze it just straight this way, it's a little weird because there are a lot of things here where ties can't exist, so a lot of the standard metrics are wrong, but people do it, and we'll talk about the right way to do it later, but just so you know, you could do it that way if you wanted. Oftentimes people do what's called a projection, and so they would say, instead of talking about people and their events, let's just talk about people to people and weight their ties by the number of events they share. Or flip it around and talk about events and the number of people who co-attend those events. And this is why this is really fun, because you can do almost anything with this. And one of my favorite examples is in hospitals. People think of hospitals as if they're one uniform organization. You show up, you get sick, and you get to the doctor and you're just drawn from the pool. But in fact, most hospitals have multiple practices built into them and huge informal networks that come out of the referrals of one patient to another. And you can map those referral networks by looking at how frequently two doctors share a patient. And when you do that, you typically find that most hospitals have 2, if not 3, internal communities, and those communities differ in the quality of healthcare they provide. And that sort of sucks because you don't know which draw you got when you got there, right? And so, for example, this is a paper that we did, a colleague of mine at Weill Medical Center did, and we were able to show that readmission rates for cardiac surgery varied by like 2 orders of magnitude over the course of which of the clusters you would be in, in a particular hospital, within the same hospital. This is a hospital fixed effects model, right? So it's the kind of thing that really can matter, and these data are there, and most people just don't even know that it's there. But you can do it with hospitals and sharing patients. You can do it with faculty on committees. You can do it with students in classrooms. And so anywhere you have people doing stuff, you have the implicit networks that come with the time that they're spending together. Now, a generalization of a bipartite network is this thing called a multi-layer network. And a multi-layer network says, if you have 2 layers, that's a bipartite network, sort of people and events. Excuse me. But a multi-layer network says we have different categories of nodes, and each of those categories of nodes has some feature that creates a relationship amongst them, and there's some opportunity for a relationship between them. So we can have relationships that occur if you will, in 3 dimensions. And so we have a within-layer tie and a between-layer tie. I'm going to talk more about how you construct these networks later. The beauty of the multi-layer framework is that it becomes a really nice way to simultaneously introduce all kinds of heterogeneity to your network modeling and to radically simplify the way in which those data are treated. There are some more scary chairs in the front if people want to use them, or you can grab over in the sides. I really don't bite. It's possible. All right, so far I haven't talked about actual data structures, so I'll do that really quickly. The traditional way of dealing with data in social network analysis has been to use this thing called an adjacency matrix, and you'll still see us talking about an adjacency matrix from time to time. No one ever really uses an adjacency matrix anymore because they're just too cumbersome, but they are nice because as a matrix you can do matrix algebra on them, and so we typically refer to them this way implicitly. But it's good to get your head around what an adjacency matrix is. And it's a double array or a 2-dimensional array with nodes down the rows and nodes across the columns, and the cell value is the relationship amongst the row and the column. So here we see that node A is linked to node B, and that's indicated by a 1. The absence of a 1 means they're not tied to each other. Right? So that's an adjacency matrix, your basic sort of standard data object that we use in network analysis. And the beauty of the matrix is it's incredibly flexible. Right? So if I want to have a directed one, I just have some of these ties above the diagonal, don't match the ties below the diagonal. If I want to have a valued one, I just replace the binary with a value. If I want to have multiple relations, I can stack this thing on top of each other. Now, when I say that we don't usually use the adjacency matrix, the reason is because most social networks are sparse. It means there's many fewer ties than there are possible ties that you could have. And it's just really inefficient to store an n-by-n matrix when most of it's empty. And so if you know that the value, the vast majority of these things are zeros, all you need to do is record the ones, and the zeros can be implicit. And there are multiple ways to do this. The most common 2 ways to do it are known as an adjacency list or an arc list. The advantage of an adjacency list is really just a rectangular data frame. This is the kind of data you're used to seeing. You have each respondent down a row and their first friend, their second friend, their third friend across the columns. Right? And this is a nice, easy way to store the data. It also has an advantage if your IDs are also your row numbers. This becomes a really efficient data structure for doing algorithms on, because you can do a walk by saying, go to the dth row, go to the eth row, and so forth. So there are some advantages to an adjacency list. If you ever find yourself in the position of writing an algorithm, you'll find yourself using this more often than not. In practice, the kind of data that we often collect are known as arc lists or edge lists, where we just create 1 column for sender and 1 column for receiver. If it's an undirected network, we don't care which one you're in. We might either have them both like I do here, or you just have one of them and tell your machine to copy it over and make it duplicated. Okay. Now, the beauty of the adjacency list and arc list format is that calculating the values is pretty easy. For an adjacency list, you just have a what and a how much. So if it's a friendship and how much do I like them, a parallel list. Or in an arc list, it's just a new column on the edge. So A to B of value 1, B to C of value 2, and so forth. Right? And so this is a very efficient way to carry the data. Now, if you have a multi-relational network, you end up traditionally storing that in a stacked adjacency matrix. And so a stacked adjacency matrix would have, if you have two relations, you'd have 2n rows and n columns. And so you'd have the first set of relations here, the second set of relations there. Right? And it's a very easy way to store the data. And again, if you did it in the arc list format, you'd have A to B, its value, and its relation there. And so here you can see that C to B is both green and red, so it's the same relation between the same dyad. That's the idea. Now, if you have a bipartite network or a two-mode network, the really only difference from the adjacency network idea is that your adjacency matrix is no longer square. Right? And so there's no special meaning to the diagonal because there's not necessarily a diagonal. And so you have as many columns as you have, say, classrooms, and as many rows as you have students, and then this tells you whether or not student A was in classroom 5. Right? Now, if you have a multi-layer network, typically what you do is you have one adjacency matrix for each layer. That's what the big squares are. And the adjacent, and then you may or may not have, whatever kind of relations characterize the relationships inside that layer. And so if it's a binary network, as I have here, it's just, blue or not. But it could be that this first, if instead of time this were, work and kinship, then work might be the number of hours you spend together, and kinship might be binary. So these need not be the same quality within each matrix. The key is the between layer linkages. So here we have what are known as identity arcs, and so it's the case that person 1, the first row of this relationship, is linked to the first row of that relationship, which is linked to the first row of that one, and so forth. And this just tells you that person 1 is the same person in wave 1, wave 2, wave 3, wave 4, and wave 5. And so here we have a temporal representation of a multi-layer network. And what's nice about this is if you want to do something like a diffusion experiment and you want to see how likely it is that if you know the dynamics of the relationship, so you know at each wave when people were friends with each other, and you want to figure out whether or not a secret could spread from one person to another over time, you can let them learn the secret in one wave and then only pass it to themselves between time and only to others within time. And so you can do these nice temporal features with these kinds of models. All right. I'm not going to spend much time on visualization. I have a whole presentation on visualization. I just want to make sure we're all on the same page. So I'm going to talk about the three classic kinds of visualizations. And so the two basic types of visualizations. Do I have this here? Where'd it go? Here we are. Why is that up? There we are. Yeah. So we typically have three basic kinds of network visualizations. The first is a tree-based layout, and so this is what you would commonly see in organizational studies as an org chart, right? So if you've ever been in any university or a business, you have a CEO, you have the people that are under them. If you're at Duke, you have the provost, about 45 layers of administration, and then faculty down here at the bottom. And the advantage of these kinds of organizational charts in theory is that you can get some sense of who's who, right? And the beauty of any of these kinds of models is that the y-axis is meaningful, right? And so it tells you something about whatever process you're dealing with. If, like I said, if it's Duke, this is authority. If it's a disease transmission, this is your patient 0, and this is the people they ultimately infected, right? A force-based layout, there's no meaning to the x and y axis. The only thing that matters is proximity. So two nodes are next to each other if they have a link linking them. And in theory, if you could spread them out perfectly, the links would all be exactly the same width, right? So a relation of strength 1 would be 1 unit long. And so then you could figure out how close people are by how far they are on this page. Now, if your network has an actual internal ordering, then this kind of layout sort of sucks. You could figure it out if you had to find the root, but it's a bad way to do it. And so, but alternatively, if your network has clusters and clumps, this kind of spatial layout automatically makes those clusters and clumps near each other, and you can find them and you can see them, and so that makes it nice. Whereas a tree-based layout for this is useless. Now, the third kind of layout is one where the coordinates are fixed by some exogenous feature, by something else that matters. And by far, the most common version of this is a map. So if I have a hospital and I want to know who that hospital shares patients with, it's nice to know that that hospital is located in Seattle, and it is more likely to exchange patients with Spokane than it is with Boston, right? And so the fact that the hospitals are physically located in an actual geographic space, you should use that and make use of it. The advantage of that is that it lets your reader usually knows something about Florida, something about California, and so forth, and so this picture makes sense. The disadvantage, as everyone who's ever done a map will tell you, is that especially in places like the United States or Russia or China, you have big swaths of the country that are just empty, right? So this big empty space here is the Rocky Mountains. This is the farmland, right? There's just nothing there. And so that doesn't mean that there's sort of less social interaction here than there is here. It's just that there's more mountains in the way. And so you have to understand there's a distortion to the network that's been put into place by using this map, and the cost of, and we're usually willing to accept that distortion because what our audience learns from it is greater than the distortion that generates it. Now, if you do a classic space-based layout to this network, you get this. And if you know what you're looking for, you can see, for example, that Southern California clusters are kind of near each other. And here's the Seattle cluster. And effectively what happens is they get bent around the Midwest. And so that's Chicago there in the middle. And where'd Florida go? Florida's up here, I think, in this set. Florida is central in a lot of hospital exchange networks because of snowbirds, because people move there in the winter. Whereas so they have one doctor in Seattle, and then when the rain stops, they go back down over here. So it's that kind of effect. If you're just curious, I've been trying to get people to do this. No one does it, but I'll tilt this windmill anyway. This fit statistic is the correlation between the screen space and the underlying social distance. I think that's a good metric for fit of a visualization. I've never seen anyone but me report it, but maybe you will. So there you go. The other sort of fixed coordinate that people use sometimes are circle layouts. Circular layouts were really popular in the 1930s when you had to use a ruler to do your network layout. Since then, there's really not a whole lot of use for it, but people still do it. I think because they don't know what else to do. A circular layout of an entire network is almost always useless. It is sometimes useful to lay out circles of parts of the network. And then you can sort of highlight the between cluster ties and sort of ignore the within cluster ties. But otherwise, don't use it. There's a version of a circular layout called a chlorogram or something like that. Don't use that either. The other thing to do is network visualizations. There are an almost infinite number of ways that I can represent this same set of points and lines. Certainly with reflection, twisting, or whatever, right? So it's perfectly, like that does no change. But even if I just use slightly different algorithms to lay it out, they're all trying to do the same thing, but they're all heuristic fits. There's no perfect mapping of a multidimensional object to a two-dimensional space, and so you have to make some kind of a trade-off to do it. And so what I encourage people to do is to use a trade-off that's meaningful to your readers and helps them learn something from the network, right? And so in this case, a classic spring embedder or space-based layout is kind of a mess, but if I weight the internal ties double, the internal cluster ties double the between cluster ties, the clusters pop out nicely. And since this paper was about clustering in the network, that was a nice thing to be able to tell people about, right? When you do that, it's probably a good idea to tell people that you've done it. It's because they might assume that there's no weighting going on here, and so that's a good data practice to be clear what you're doing. If you're sharing your code and such, like we're all supposed to these days anyway, that shouldn't be an issue, but just be sure you're clear what you're doing. But this is all another way to say is the other thing that always freaks people out when they first start playing with networks is that I'll be sitting down next to someone and they'll say, I can't see behind that, and I'll just grab the node and move it. And it's like you think I might have busted their eggs or something. It's like a really bad thing to do because we've all been told don't mess with your data. Mess with your data. I go in and move things around if it makes your story clearer. You have my permission to do that. Please. Yes. They're not available right now, but I can make them, like, I can send people an email afterwards. And if we have a Google Drive. I just don't think we advertise to the Google Drive. So, Madeline, if you wanted to send the Google Drive link to people and share it with folks, make it a public. I don't know if you are allowed to make that drive public or not.
Yeah, I don't think I have access to make it public.
All right.
That might be.
I'll send a link out to everyone on the list after this presentation. All right. The other thing to do with networks is sometimes the best network image is not a network image. Right, the best network image is an abstraction from a network image. This I stole shamelessly from Peter, who's in the back, who's laughing at me. But this is what the co-voting network of the US Senate looks like. It's useless. But if you sort the adjacency matrix properly, you can see this beautiful sort of clustering, and then the cross-group ties actually become meaningful, and you can ask questions like, who the heck is that, right? And make sense about, well, there's somebody here who's doing this job, and it's, you can see him there a little bit, but it's just nicer that way. The other abstraction you might be interested in is a process on the network as opposed to the network itself. So this is the geodesic distance distribution. So if you were to do a random walk from every different node in the network, and you go out one step, you get the degree distribution, 2 steps, you get the 2-step distribution, and so forth. And this tells you sort of a way of thinking about how quickly, what the forest of possible paths through this network looks like. And you can see that most of the paths through this network are pretty fast. Within 3 or 4 steps, you reach essentially 90% of the population. But there are clearly some really peripheral nodes here that it take a long time to reach everyone else. And that's kind of an interesting feature. Maybe it's irrelevant for your process, but who knows. Similarly, if you have a spreading process on the network, then maybe you don't need to see the whole network. You just want to see what the spreading tree looks like. And so you can map that directly. Okay. And we just already talked about that one already. Questions or comments on that? I'm a visualization nerd, so I like playing with this stuff a lot. I can geek out over that for a lot if you want. All right, so there are some basic network metrics. A lot of what network analysis is, and this is the joke I give people, that network analysis isn't particularly complicated. It's all sorting and counting, right? And so the vast majority of network metrics are just very smartly sorting and counting. And so if you know how to sort and you know how to count, you can do network analysis. How exactly we sort and count kind of depends on a few things that we care about. And so we're going to talk about what I refer to as sort of the basic foundation network metrics. And what I mean by metrics are scores you put on either the graph or the node that you're probably then going to use later to either convince someone to buy your product or to run a model, right? So that's the kind of thing that the metric is used for. And the kinds of ones we typically focus on are some volume features, some reachability or path things, this whole world of centrality, and then some kind of clustering. And we're not going to talk about clustering much today. I'm just going to just briefly do it. So most of our networks are sparse. By sparse, what I mean is their density is really low. And density is the average value of the dyads in the network. So if it's a binary network, it's the proportion of edges that are present. And so that's traditionally what folks are used to thinking about. And so if I have a density of 0.3, it means that 30% of the edges are present and 70% of them are absent. Or 70% of the dyads are null and 30% of the dyads are linked. For a valued relationship, that percentage metrics doesn't make sense, but the calculation is the same. You just take the average of all the observed ties, and that gives you the average of the observed ties is 1.2 out of the set of 20 ties that could be there. Usually, we discard the diagonal when we don't care about ties to ourselves when we're talking about density. That tends to be irrelevant, but otherwise, you can if you have some kind of relationship where that's sensible. Like you could do a hospital exchange network where you care about inter-hospital as well as intra-hospital ties, then the diagonal would make sense. Okay. It ends up being the case that I think the density is the traditional measure of volume in networks. It sucks. It's an awful measure of volume in a network because networks have this nonlinear denominator. And so the case is that whenever I have n nodes, I have almost n squared possible ties in the network. And so the denominator of the network, of the density score, grows at the square of the size of the network, but the numerator grows linearly. And so your density ends up being non-linearly related to the size of the network. And no one knows what a 0.0006 density means. Like, is that big or small? Well, I don't know. Do you have 1,000 nodes of your networks, or do you have 2,000 nodes of your network? And so what I typically use and recommend people to use is just average degree. And so the degree of a node is the number of ties, the number of other nodes adjacent to that node is its degree. So the number of friends I have is my friendship degree. The number of romantic partners I have is my romantic degree. If it's symmetric, then then my out degree, the number of ties I send, is equal to my in degree, which is the number of ties I receive. If it's not symmetric, those two measures will be different. If it's a valued tie, we talk about the weight of a node. So a node's weight would be equal to the sum of the ties across its rows. So this row, node E, has an out degree of 2. It's tied to 2 nodes, but its weight is 6. So size and average degree are really the only 2 numbers you need in terms of volume. In terms of connectivity, the sort of path metrics, I really like just to remind people that what makes network systems are the fact that edges aren't connecting just a dyad, but they're connecting one dyad and another and another and another. And it's this path feature that makes networks interesting, right, beyond just the social support idea. And so anytime you can imagine sort of a wandering through this space, right, that's going to give you something potentially interesting. Graph theorists have categorized these kinds of ways of walking through a network in different ways. And so a path is a walk through a network that starts at one node and ends at another node. And when you reach your own node again, you stop. So you don't ever go backwards on a path. On a walk, you can do whatever you want. So I can go from A to B to C to B to C to B. I can just walk back and forth here before I go elsewhere. A cycle is a path that starts and ends on itself. And those are really interesting. It turns out that cycles mean a lot in networks. They're the foundation for lots of things that we care about, particularly clustering. The one path that we really care about a lot, at least empirically, is the shortest path. It's called the geodesic path. And so that's the shortest possible number of steps it takes for me to get from one node to the next. And so in this case, I can go 1, 2, 3 steps to get to E, or I can go 1, 2, 3, 4 steps to go to E. So A to E's geodesic is 3. It's that shortest possible path. And it turns out there are 2 of them. I can go from A to F to C to E, or A to B to C to E. Both of those are length 3, but there are 2 different ways of doing that. We refer to the set of all nodes in a network where it's possible to trace a path between them as a component. So a component of a network is the maximal subset of the network for which it's possible to trace a path from one node in that component to every other node in the component. We think of these as just connected sets, right? So if you look at the plot and you see that there's no gap between any of the nodes, that's a component, right? Whereas this is one component, that's a little component, that's a little component, that's another little component, right? And so a component is, as soon as you're sort of tracing through the network and run out of nodes to reach, you've reached the end of your component. Right? If your network is connected, or directed, excuse me, then you can distinguish between strong and weak components. In practice, that's rarely relevant for most of the work we do. There are a few things where it matters. Most of the time, we typically think about weak components versus not, and then the amount of volume between pairs when we talk about reachability. I'm going to skip this part, other than to say that most of the time we care about this connectivity in networks. One of the things we care about is whether or not the network is broadly connected or star connected. If there's a few hubs that if you remove them, disconnect the network, these are cut nodes. And those can often be really important, particularly in disease diffusion problems. If we're interested in stopping the spread of a disease and we know that our network has these hubs, then ideally we would find those hubs and vaccinate them, for example. Already explained what the geodesic distance is. It's just the set of shortest paths. If you've ever played the Kevin Bacon game or heard the notion of a small world, that's really all this is. So 6 degrees of separation is what that is. The geodesic distance is, we use it because it's easy to calculate. There's a brilliantly fast algorithm called breadth first search that takes you from one node to the next, and it gets you the geodesics, and it gets you the distance anyway quickly. I'm not at all convinced that most social processes happen on geodesic distances. I suspect that would be really remarkable if that were true. And so in fact, In practice, the more interesting distance is probably a random walk distance, because I suspect that's more representative of what really happens in the world. But it's only been recently that we can calculate random walk distance at any kind of speed, so we typically don't do it. So traditionally, you're going to say geodesic distance, and that's when I talk about distance, the default, if no one says otherwise, the distance they mean is geodesic distance. I'm going to skip through some of that. So there's more of this in this slide than you need. The distance tells you how far a node is from every other, so the number of steps it takes to get. If you really want to know how cohesive a network is, you need to know how far they are apart and how many ways they're held together. So it's both distance and redundancy. If you think about this when you're trying to drive in your commute, right? If you're stuck in traffic at some spot and everyone else is stuck on that same spot in traffic, that's usually because you're on the same shortest path together and there's no alternate route. If there were lots of alternate routes, you wouldn't all be stuck there on that one traffic jam together, right? And so redundancy is this capacity to have multiple routes around the set. There's some formal measures for that. I'm going to skip over what those formal measures are, just to say that if you have multiple paths, the network is more connected than not. And again, you can look up this on the slides if you want to get there. Centrality scoring is the idea that we care about nodes not just by sort of how close they are to another node, but whether or not where they fit in the overall shape of the network. And so centrality scores are a set of metrics designed to figure out if a node is on the edge of a network or the middle of the network. The problem is the meaning of edge and middle differs depending on what kind of centrality you're talking about. And lest you think I'm ridiculous, this is someone else is even more ridiculous than me, and they put together this map of the different kinds of centrality measures there are. There are hundreds of centrality measures. And some people look at this and say, well, that's just ludicrous. That must mean that there's nothing to this. I actually think this is actually one of the more interesting pieces about network analysis, because what this should tell you is that what I'm doing when I'm calculating a metric on a network is operationalizing a social process. I'm trying to figure out what it is that creates sales or makes people sick or makes people trust somebody. And there's something about their pattern of relations that does that makes the network do that for them. And I map that onto a counting and sorting procedure and call it centrality, right? And so that's really what it is. And so some of these centrality measures, all of these purple ones are betweenness centralities, right? They are all focused on this notion that a node matters because somebody has to go through them to get to somebody else. And you could do it through multiple loops, you could do it through a weighted set, you could do it through a threshold, right? Each of these has slightly different sort of elements about that separating feature of betweenness, whereas degree up here is just the number of ties you have, right? And so it says that I'm important because I have lots of friends, or I'm really sad because everybody hates me, right? That's a kind of, that might be what it is, right? So you can imagine that there are certain social situations where the kind of thing about relations are really simple to calculate. So like how much someone is disliked is probably a good indicator of their mental health. And that's all you need. You don't need to know where they fit in the overall sort of hierarchy. You just need to know how many people dislike them, right? Whereas if I really care about who's spreading secrets, then I might need to know betweenness, right? And so these different kinds of social processes are going to get mapped onto different features. If you need to know anything about centrality, there's sort of the big four measures. There's degree centrality, which is the number of people you're tied to. And so here we see that this node is tied to 7 people, and each of them are tied to 1. And degree centrality has some weirdnesses we can go over later. Closeness centrality is the second, which just says if I have a distance matrix, then I say how far person I is from person J. I add that up for the entire row of the network. The J is on, and that's their closeness centrality. That just tells you on average how many steps it takes me to reach everyone else. If I have, really bad body odor and I have really strong closeness centrality, everybody smells me, right? That's the radiation sort of model of closeness centrality. Awful analogy, but now it's stuck in your head. See how that works? And so the notion of closeness centrality is that you just spread out through a radiation, right? But there's no real structure there. It's just pure distance. And the third one that you sort of need to know is this idea of betweenness centrality. And betweenness centrality says that a node matters because every other node has to go through it. So any path in this network has to go through A. So A can charge whatever price they want, right? So if you were the Phoenicians in 500 BC, this is what you did with tin, right? You were the tin monopolizers in the world, and that was a great position to be in. But once you found your way around the Phoenicians, you didn't need them anymore, and you fall away. Between centrality, I'm not going to go over some of the features around them. The reason that again, you can look up some of the details that we went over in the earlier versions of this class, but I do want to remind you to not necessarily treat these as single indicators. That part of what makes centrality interesting, and the fact that we have all these centrality scores, is that you can use them in combination, right? So if I have high degree, I have lots of friends, and really low closeness, that means that none of my friends are friends with anybody else that matters, and we're off in our own little corner somewhere playing Dungeons and Dragons, and sort of we're off on the side, right? So that's a different setting than someone who has really high degree centrality and high closeness centrality, because that person reaches everyone quickly, right? And so this is the way to think about these things as combinations that describe this multidimensional set. That was literally the world's fastest introduction to the big three. I forgot the fourth one. The fourth one is eigenvector centrality or power centrality. This says that I'm important if I'm connected to other important people. The sociological version of this, the one that we always use, is called Bonesich power centrality. And so this is Phil Bonesich's notion, and I like this measure because it has this little coefficient on it, this beta coefficient, which allows you to essentially say how much of the radius of the network you want to care about. So if the beta is set to 0, it's degree centrality. If it's set to 1, you're weighting everyone all the way out to the full reach of the network. But you've used this measure today, because this is just PageRank or eigenvector centrality. They're all fundamentally the same. They're saying that my centrality is a function of the people I'm tied to. So I'm important if I'm tied to important others. Questions on centrality? Again, that was the world's fastest treatment of centrality. If all of this is brand new to you and you've never seen any of this before and this isn't review, let me know and I'm happy to point you to some other features, or don't be shy to ask questions. The other thing that you will typically do in a network is find groups. You find clusters of various sites and sizes. This is known as community detection. I'm not going to talk about community detection at all today, other than to say it's going to happen and we're going to talk about it a lot tomorrow. I said I wasn't going to talk about it, but I kept the slide up there anyway. Communities, I'm going to keep the slide now that I have it. Communities are finding groups that have this really special characteristic, which is that all of the volume of these sparse net matrices falls on the diagonal. And so we have these groups of people that are all friends with each other, and if I were really smart in how I sorted and counted, I'd be able to arrange the adjacency matrix such that there's a lot of ties on the diagonal and no ties between. Right? That's what classic community detection is. How you get there is a pain in the ass, but we'll talk about that. The other way to sort and count is to ask about roles. And now when we're thinking about roles, remember, we went this parent versus child, student versus teacher. We want to find groups. We don't necessarily want to find groups where all the density is on the diagonal. We want to find a particular pattern that is characteristic of the setting we're in. Right? And it might not be block diagonal. And so in this case, for example, the parents and children, we want to be able to given a set of relationships, could we induce that by finding set? And the way you do it is this big sort of set, and we're going to do this in depth on Wednesday. And so we'll talk about both of these kinds of group finding things. All right, that was the world's fastest collection of work on metrics and so forth. And then I'm going to just introduce a little bit about models if in the next, I think I have a half hour on the schedule, if folks are still with me. Or do we need to stand up and say hi to our friends real fast? Let's take 3 minutes. Stand up, turn around, put your right foot in, put your right foot out, that kind of thing. Take 5 minutes, introduce yourself. I'm really torn between my two roles of trying to pull people together and create community and yet provide information. So I don't know if I should be squashing conversations or not. But if we run over, it's just your fault, so that's fine. So I've just taken off thought entirely. So, all right. So we're going to just wrap up this quick sort of network revision, remembrance, reminder sort of session with this notion of models. And so you're going to hear a lot over the course of this week of this idea of network models. The problem is that phrase by itself is pretty meaningless because it turns out that there are a lot of different network models that all mean different things. And so we have models of networks, we have models on networks, and we have models that use both the networks of and on, right? So all of these things happen simultaneously, and when people talk about, I'm going to model disease flow, you really have no idea what that sentence means until they put some reality behind it. So I want to spend just a little bit of time without really going into any detail. There's more detail, again, more detail in the slides than you're going to get in my presentation, just sort of reminding us what the different kinds of models are and what they might mean. Right, so the first kind of network model is usually the model of something through a network. And so diffusion is the archetype here. And so we think about the primary route from networks to health is via diffusion. Well, then we start with this notion of things moving through a network. Now, compartmental models have been most of our lives for the last 3 years, right? So we've seen various and sundry versions of the classic SI model, or the SEIR model, or the SIS model, or a compartmental model by age, right? There's thousands of these now that have been done. And these are really useful. And they have what's under the hood is essentially inside of each of these buckets, the movement from S to I, is a homogeneous network. The idea is that there's just, everyone has an instantaneous probability of being connected to everyone else within the same set. And because that network is so simple, right, in its structure, we can actually use a single parameter to describe the movement from there. And if we need a little more complexity, we just say, all right, let's say beta I for young people, old people, middle-aged people, and bald professors, right? So you can have as many compartments as you want for whatever setting you want, and just make it simple within, and then you only have to worry about the complexity between. And so I don't want to discount these models because they really are very useful for some kinds of spreading, like COVID, they can be quite useful. But there are times when we think that this picture of the world, this kind of random network assumption, doesn't match the reality. So that variance is so stark that it's worth actually having some element of the network itself. And so what diffusion models do on networks is they say, let's just focus on a single parameter, but let's put that parameter in the network. And so we have some likelihood that I transmits to J, that's what I'm calling Pij here, and that's a parameter that sits on the network. And it's usually some function of the strength of the network tie, the amount of time people spend together, the kind of relationship it is it a work relationship, is it a family relationship, or what have you. All of that can get turned into a probability. Once I know the probability, if the probability is 0 or really low, the network this diffusion never goes anywhere. If it's really high, it can go lots of places. But what's beautiful about this kind of a setting is that if you start at one place, in this case I started with the exact same node, and just change that probability, you get these wildly different spreads of the potential for the disease to move. And this kind of stochasticity is interesting because it's working over this kind of a clumpy structure. So it gets in, it moves, it gets stuck, it doesn't move. And when the when the dynamics are really strong, there's nothing here that's all that interesting. It just goes from, everyone's fine, someone coughs in a large seminar room, and everyone is sick. Well timed, that was a good, I'll pay whoever did that later. But there are other times when there's the dynamics are really interesting. And one of the things that's not evident in this slide because you can't see it very well is that sometimes down here at the bottom, even though these look like there's nothing happening, you get rare events. And these rare events can happen that take a network that should be nothing happening, and all of a sudden the infection takes off. And so understanding rare events, you can't do that with compartmental models, but you can do it really well with network models. And so that's the kind of thing that's worth thinking about. Now, if you want to ask yourself what kind of diffusion features matter, we're going to go over a lot of this stuff in detail on Friday when we talk about the diffusion set. Those are in this slide here, but the main thing to keep in mind is that you have the reachability idea we talked about before. Is it possible for one person to reach the other? Are they in the same component? How far away are they? How much clustering there is, and so forth. And I'm just going to skip over these slides because you've seen them before, but just to point out that again, that you end up with different shapes of networks have these kinds of features in common. The thing that makes a sexual network, kind of slow for spreading of a disease is it has these kind of really sparse ties, whereas drug sharing networks have these really dense clusters. And so the structure of that network contributes to the speed with which things move through it. And the final element here that I have on this list of these sort of 5 things that matter is this notion of star spreaders. And again, this is really what I want you to think about there is, in contrast to compartmental models, network models allow for node-level heterogeneity. So you have this why nodes are not substitutable necessarily. It's the case that people differ in their practices, and that practical difference matters with the spread of the disease. Now, when you think then about a network model, right, for diffusion, we often think about also the network, the model of the network itself. And one of the key features for diffusion is this notion of assortative versus disassortative networks. And this is the extent to which people with the same volume interact with other people of the same volume. So if I have lots of sexual partners and my partners have lots of sexual partners, that's known as an assortative mixing situation. So people that have a small number of ties are tied to people who have a small number of ties. People that have a lot of number of ties are tied to lots of others. A disassortative means that people with high degree are connected to people with low degree. And this is a fundamentally different shape, right? You can just see it when you look at it. And it's one of the key sort of parameters here that often goes, it's well known in the sexual network, sort of HIV kind of literature, but you don't hear much about it other than this sort of informal notion of star spreaders. But it's really not the star spreader idea. It's not that some nodes have high degree. It's that those high degree nodes are uniquely connected and spread around the network in a way that links them to other people, and it's better to think of that as a disassortative setting. All right. One of the things that's kind of interesting about networks, this is an old slide that Martina Morris and Jimmy, I think you were involved in this at the time, put together, where we were thinking about the spread of a network, of a disease over a network. And what does the foundation of the network look like? How does that come to be? And you can imagine different types of populations, right? So populations with small numbers of nodes, and it's a sexual network. And so no one has more, assuming that no one has more than 3 ties, right? And so, but all that happens over the course of these 4 different panels is that we shift the number of people who have 1 tie. Some of them now have 2. So the number that has 3 stays essentially the same, if I remember correctly. But the number who have 2 goes up a little bit. And so the average degree goes from 1.68 to, what is it? My eyes are too bad to see that far these days, to 1.87. And you go from a network that has lots of little components to a network that has one giant connected component. And what this is a feature known as the emergence of a giant connected component. And this is a classic feature of random graphs. There's always this threshold in terms of the average number of sexual partners or the average degree of a network, that at some point along the distribution of average degree, the network goes from disconnected to disconnected, and it reaches this threshold, this tipping point, and radically jumps up to where everyone's connected to everyone else. This is a general feature of all networks and a feature of the volume aspect on networks. What differs from network to network is the shape of the degree distribution. So what's unique about this particular case, and as you can tell, I've cherry-picked where those 4 slides came from, right? That when you have that really short degree distribution, as soon as you sort of use up a lot of those 3 degree nodes, they're going to connect all of your other sort of 2 and 1 degree nodes, and you're going to rapidly reach this super sharp threshold. Whereas if you have what's known as a scale-free network, where you have a few people that have hundreds and hundreds of ties, but most people have a few, those people that have hundreds of ties can pull in lots of isolates, one at a time, a little bit at a time, and you sort of aggregate the network slowly. And so you still get a threshold, and it happens at a lower space, but it emerges much more slowly with respect to this average degree set. Now, why am I giving you this? I'm going into so much detail in this old case. It's because when we think about network models, the degree distribution and the assortativity versus disassortativity is a key element of the network model itself. So what kind of network is it? People will say, I have a scale-free network, or I have a small world network. That's what they mean by a network model. What they really mean is the shape of this underlying distribution that then makes it possible of this distribution, which then makes this kind of thing possible. Is that clear? I don't feel like I explained it well, so I'm going over myself. Now, there's an entire separate side of networks diffusion that has to do with the dynamics, with concurrency, and with the spreading in time. I'm going to skip over that for now because it's a bit ridiculous to go into depth at this speed, except to say, and I think I can have it right here, that once you know the timing of relations, the exact same contact pattern here in red can lead to radically different potential spreading regimes depending entirely on the timing of relations. And so it ends up in the case in this little example, you end up with a difference of something like 2 orders of magnitude. And it's just because you can't get sick from people who have sex with your partners after you've left them, right? So you have to have relationships unfolding in time. And that kind of temporal feature is really hard to see in most of the data we collect, because most of the data we collect in coarse timings. We say, who have you slept with in the last year, not when did this start and when did it end, right? And so when you collect data in waves, you necessarily get very clumpy data temporally, and that clumpiness in the data is going to make it hard to see. So a lot of these kinds of nuanced sort of features of the spread that can really make a difference in how fast disease moves through a population. If you're interested in this process, it's this whole thing called forward reachable paths, and there's a whole piece that we've done on it, and I'm happy to go into it in depth, but I'm going to leave it aside for now. All right. The other kinds of models that we have are models of the spreading process itself. And so the process that I've been describing thus far is a classic biological disease spreading process. You have an infected person, they bump into a susceptible person, and with some probability, A passes to B. For social contagions, that's often we often use that model, but it's often not a great model, because we suspect that people have a meaning-making process hidden in their heads that we don't have access to that governs their likelihood of not just being susceptible, but acquiring and actively sort of adopting whatever is moving through the network. So the adoption process is active, not just the spreading process. And if you've ever seen a street side, anybody from Chapel Hill here? Is the pit still active? Is the pit preacher still there? Anybody here? When I was in Chapel Hill, there was a guy that was every day would stand down in the pit with his Bible in one hand and yelling at the top of his lungs that we're all going to hell in a handbasket, right? And so that kind of fire and brimstone preacher, right, is all about infected trying to go to a susceptible, but no one's adopting, right? And so, that's a good example of the active side of adopting, right? If you don't have someone out there who's willing to take Jesus into their life as Savior, right? If they're not going to do that right there, they don't have that kind of adoption set, then it's not going to work. So you need to have some model for what makes people adopters. And the Everett Rogers sort of model of this, the original diffusion of innovations model, was one that said that people have different internal thresholds. And it's a piece of your psychology. It varies from person to person. And whatever your adoption threshold is, it's unobservable, but we can infer it from the pattern of adoptions. A few others have come up with this notion. Damon Santola and Michael Macy, for example, of thinking that, well, what determines the adoption set is really a structural feature, not a psychological feature, and it has to do with the peer pressure, with the number of your peers that have already adopted. If many of your peers have adopted, you feel that pressure and you're more likely to adopt in a well. And this has been sort of all categorized under this idea of complex contagion. And the notion here is that it's not enough to bump into a single person who is infected in order for susceptible to pass over, but you have to have some large number of people who are infected to expose to you to get it. And so for social contagions, you might have this kind of complex adoption model, which requires multiple others to have the good before you're willing to adopt the good. The classic example in social contagion is cell phones, which is a little dated now for all of us, of course, but being the first person with a cell phone is pretty useless, right? If no one else has it, it's kind of cool, but, no one really cares. Whereas now, if you don't have it, you're out of luck, right? So the value of something takes on a benefit the more other people have it. This sort of network complementarity, it's called. And so the way the complex contagion works is that if a pair of people have the good, we say I only adopt if at least 2 of my peers have the good. Then if we start here, then that means that this person can't adopt because only one of their peers does. But this person has 2 peers that adopted, so they adopt next. Now this person would adopt. And these 2 can never adopt because they don't ever have the opportunity to adopt from 2 other peers. Right? So that's the notion of complex contagion. And the way you can imagine thinking about how this trickles through a network and why it's harder than simple contagion. If I were to start with this connected pair, this set of nodes for which at least 2 of their alters have already adopted is always going to be limited by the degree of the set they're connected to, and it spreads throughout the network. And what's kind of fun about this is that kind of contagion can actually lead to a very different type of pattern, right? And so this is, if you were to run a simulation over a set of one of these networks, and I think I did it over a bunch of these networks, what you find is if I seed the network with a connected pair, so it's at least possible for this thing to get started, most of the time, it never goes anywhere. And it never goes anywhere because it runs into this kind of a bottleneck, right? And once you get there, it can't pass that bridge. But if it does pass that bridge, almost everybody gets it, right? So you either get no one getting the disease or adopting the benefit or everybody adopting the good. And that's kind of an interesting characteristic of social adoption that distinguishes from disease adoption or disease diffusion. And it's conditional on some other sort of features of the network. Now, it turns out that there's lots of other features other than this complex contagion adoption model that govern the likelihood that an individual will adopt an idea or a belief or a practice that's different than the way that disease moves through networks. This falls under a rubric we call peer influence dynamics. And Craig Rawlings is going to be talking a lot about that later in the week. He's going to do a nice session on that, as well as, and he will talk about the substantive feature of this and when it happens and why. And we'll also be talking about how you model it statistically using the stochastic actor-oriented models, or SOAMs. So the other use of the word model in networks has to do with statistical model. And so the statistical model for networks are fundamentally random graph models. And so there's this whole theory of networks in mathematics known as random graph theory. And random graph theory assumes essentially that you have an adjacency matrix where you flip coins, right? But you don't necessarily flip them just at random. If you flip them just at random, you have this. But I can flip them in a special way, right, with a little more bias on some edges than the other. And that gives you a whole family of different possible network models. And I will go over this in depth on Thursday. All right. I want to end today, my bit today, before I turn it over to Leanne and Gabe. There's just some thoughts about things that I still think are interesting problems that we might think about doing in the future, sort of open problems in networks. These problems, if I'm honest, I sort of hope you guys do, because I'm going to quit this job eventually. Some days it feels sooner rather than later. But I just want to put out these ideas, and this is like my completely idiosyncratic sort of notion of what I think is useful to be focusing on over the next few years. Some of these problems have been more or less solved, most of them less solved. But again, I think there's some interesting questions here that you might be interested in playing with. The first is this idea of large-scale social diffusion. I think that our models for network diffusion are still fundamentally pretty limited to this kind of one-wave contagion piece. And the characteristic of these one-wave contagion models is a single hump and a single diffuse. And what's crazy, of course, is that we've all been through a disease process for the last 3 years that looks nothing like that. Now, I can get this kind of curve if I add some funky feedback features or deliberately distort the model to fit the data, right? But from first principles, get this kind of curve is actually pretty difficult. The best way you can do it is to involve some kind of a social feedback process where your agents are looking around and they're not the dupes of the situation around them where they just happen to bump into a disease and get sick, but they look around and they see some sick people and they walk to the other side of the room, right? And that kind of dynamic feedback where people are in real time adjusting their practices to the spread of the disease really thwarts our compartmental models in a way that we're not very good at doing right now. And so I think thinking about networks and the ways in which we have competing diffusion processes, diffusion of information while we have simultaneously diffusion of disease, for example, is a great way of thinking about how these processes would simultaneously reinform each other. And I think building, again, from first principles, a way to do that would really be interesting and I think would be really valuable. I think the other thing that we can do is think about missing data. This is a problem that I've spent a lot more time thinking of than I care with. And it turns out, as you're going to hear tomorrow when I give this part of the talk, that it's a really hard problem. And it's one of these problems that has a really elegant statistical solution that doesn't work near as well in practice as we think it should. So there you go. I think there's a good moment for econometricians and statisticians and social theorists to think together in ways that they haven't thus far. which is that we have now statistical models for causal identification that are really strict and really powerful, but also really sociologically naive. The thing that sort of makes social life interesting to many of us in the social theory world is that things are what we call overdetermined and reinvested. And so the idea that there is a single cause that you can uniquely identify for making something happen is just never true, right? If you've ever done an interview with somebody where you ask them why they did it, and you ask them that question twice and you get two different answers, you know that they, in fact, don't know what caused it, and they probably are unaware of what caused it. And so the notion of what's actually causing something in a medical RCT sense versus the sort of embodied action that people engage in to motivate their behaviors and create meaning in the world that they live in, I think that those two things are far from each other. And the way I characterize this problem is that we have this notion of reciprocal causation, where people are mutually causing each other and their behaviors are mutually causing their interactions. But we treat that as if it's two separate features that are occurring sort of distinct from each other and that are in fact separable. And I think that we need methods that are more akin to this kind of truly joint causal feature as opposed to separable, unique cause features. And I don't know how to do that. I don't know if it's possible to do it from an actual estimation standpoint, but I think it's important to think through substantively. I think that we have underused roles, and so you're going to hear me talking about roles a lot in this talk because this is the advanced version of this class, and I want you guys to go out and do this work. So just know, this is just fair warning, you're going to get a lot of this week. But it's really, I think, an interesting way to think about the world around us. None of us are unidimensional, right? None of us have a single relationship with anybody. Many of you in here are former students of mine, but you're also colleagues and collaborators, right? We've eaten dinner together and we've shared offices. So there's all these other sort of layers of meaning that go on to everything. And that's true for every relationship anyone's ever been in. And I think that we now have some formal tools for doing this, but I think the substantive tools for doing it kind of died with structural anthropology. We have the real theory behind this has gotten, there's a sort of one branch of it that's gotten really technical called generalized block modeling, which is kind of cool mathematically. It has all these different types of equivalencies that you can play with. But thinking about it in terms of the rich sort of notion of what a role is and what obligations and meanings mean for pure actors, that hasn't been explained much. And I think in the health world in particular, there's a lot of room for this. So what does it really mean to be a patient or to trust your physician? And are physicians substitutable in trust? Or does it require a certain kind of relationship that has to be built up? Like, can you do drive-by healthcare and actually have trust in an institution, or does it have to be trust in a person? And that's just the simplest possible version of where this happens. And I think because health is so fraught with people's notions of life and death and wellness, that it has a lot of meaning sort of naturally coming out of the gate that we're leaving on the table. And I think it would be really fun to think and exploit that. I think that there's something about a network life history that's worth thinking about. And so we should be able to think about relationships unfolding over a life course. And so that we have, there's a reason that high school movies are so important in sort of like the American culture. It's because like that moment in your life course is the first time your parents let you out of their sight and you get to sneak a kiss with someone under the bleachers or whatever. And it's like this kind of secret and sort of developmental thing combined with the fact that your brains are finally actually rewiring, right? So there's all kinds of intersections here that make that moment in your life so much more important than it ever should be, right? And yet it has this play for how we sort of think about our life course. And I think that has to be true for romantic relationships. It has to be true for work relationships. There's a reason that full professors are grouchy at faculty meetings. Like, I've just been around you people too long, right? And so assistant professors are all sort of shiny-eyed and ready to go. You can have it, right? So this kind of notion of a life course of relations is something that we want to play with. And I think that we can build it into our models as well. All of this is by way of saying that in the context of social networks and health, that the relational dynamics as they actually unfold in social settings should lead to health behavior and network mechanisms, right? Not just network methods that correlate with the health outcome, but with thinking about what it is that actors are doing and settings are enabling to create more or less health in a setting. And I think that if we as health theorists could explicate what these kinds of mechanisms are, we'd do a lot better at sort of getting this sort of model out to the set. So this brings me to my third point, which is what do you do to get some of these pieces done? I would love to see a return to community studies. So in the 40s and 50s, it was the sort of golden age of network community studies, where people would get whole hosts of graduate students and teams. They'd go to a community, they'd interview people, they would take jobs in the community, they'd live there for a few years even, in the case of one of the studies. And they would get to know the setting and build these big multi-relational settings. Now, I don't know if that's certainly not feasible in the kind of academic life course that most of us live in. But thinking about social settings as a full ensemble of community relations is worth doing. And it might be that community becomes a hospital. It might be one nursing home. It might be one school that you actually integrate the students and the faculty and the staff and everyone together. But by getting into that whole setting, you sort of sidestep this notion that we have a single X and a single Y, but instead we have a constellation of events that co-constitute each other and create the potential for healthy outcomes. And community studies did that really well. A lot of good qualitative work does this. Now there's a lot of bad qualitative work, but really good qualitative work takes seriously both the meanings that people give for the work they do and the context within which those meanings are generated. And if we do that well, I think that's in many ways the most powerful work we can do. Now, perhaps the easiest way to do this is to take advantage of what the modern world has that the old community studies never had, which is the electronic traces we all leave around. So digital traces and digital sort of ethnography is something that we should be thinking seriously about. And so there are lots of ways to do this now that are much less intrusive than they used to be. So, I mean, the one problem with the old community study idea is you had some foreigner sitting in on every, meeting, and they were really an outsider looking in. The beauty of me just putting an app on your phone is that you don't even know I'm there, right? And so Google probably does this to us already, right? So you can see what's there. So there's got to be an ethical way for us to, put a trace on people, but finding a way to take the digital traces that we all leave of our lives, and in many ways very deeply, and finding a way to link those together with actual behaviors would be nice. Now, there's a lot you can do, I think, in some settings with electronic health records for this. And so in a community like Durham, like Duke Hospitals has a monopoly on everybody in this county who goes to a doctor. So if you go to a doctor in Durham County, odds are really good you're in the Duke Electronic Medical Records data set. And so we have, in many cases, the life course of each person, their kids, right? And, at least until those kids graduate, all the way through this set. So you have lots of opportunities to link people together in a full setting. And if we can combine that with the contextual data we have about the city and about the opportunities and employment and so forth, you could really get a lot out of that. So there might be opportunities for people like me who would rather be in front of a computer than in a meeting or actually trying to do an ethnography to do this kind of work without having to actually go out and talk to a real human being. And that's what I'm meant by the electronic traces at the end. So I'm going to end there, and I'm going to really first encourage you to have fun this week. I'm so glad you're all here. It's really great to see everybody. We're going to switch over now. We'll take a quick break. And I think next, is it Gabe or Leanne? Leanne's next. We're going to do next is a little bit of review of how to use R. So if that's for those of you that haven't looked at R since last time you were in this meeting or haven't looked at R at all, that's a chance for us to get just to be on the same language, because the rest of this week you're going to see a lot of R scripts that are going to be shown and so forth, and just give you a sense of what's going on with that. And then we'll end today with Gabe presenting a new set of software that we're Gabe and Tom, and is Kieran here? I thought he was. Is also going to be help presenting that. So, questions, comments, thoughts before we set loose from this first session. Awesome. All right. Thank you.